Welcome to Dr. Sherry's Astronomy channel. The topic of this episode is at last, a discovery. A star that evolved directly into a black hole. A research team led by Dr. D at Columbia University has, for the first time ever, confirmed that a star evolved into a black hole without producing a supernova. This result was published in the journal Science, in February 2026. From observations so far, black holes are mainly divided into two types, based on their mass. One type is the supermassive black holes, that reside at the centers of galaxies. The other type is stellar mass black holes, with masses of just a few times that of the Sun. How these black holes form has been a long-standing mystery. But many stellar mass black holes are thought to be born when stars more massive than the Sun reach the end of their lives. This diagram summarizes the evolutionary path of a star, from its birth to its final fate. On the far left, the stellar nursery represents a place where gas and dust gather, and new stars are born. From there, a star passes through the protostar stage. And once nuclear fusion ignites in its core, it begins to shine steadily. A star can remain stable, because of a balance between gravity and pressure. Gravity tries to crush the star inward, while the heat produced by nuclear fusion pushes the gas outward. As long as these two effects are in balance, the star can maintain a roughly constant size and brightness. In this diagram, the lower region shows the evolution of relatively low mass stars. And the higher you go, the more massive the star becomes. Stars like the Sun, and stars even lighter than the Sun, evolve slowly over a long time, using up their fuel little by little. As evolution proceeds, they swell up, become red and large. And in the end, they gently release their outer gas into space. That ejected gas spreads out faintly, and is observed as a planetary nebula. And at the center, a white dwarf remains. This is the burned-out core that is left behind. Along this pathway, gravity never becomes strong enough to crush the core all at once, so there is no spectacular explosion. On the other hand, massive stars have extremely high temperatures and pressures in their cores, so they burn through their fuel in a short time. Nuclear fusion proceeds in stages. And in the end, an iron-like core is built up at the center. But iron does not readily yield energy through fusion. So the outward push that had supported the star becomes weaker. At that moment, gravity wins, and the core collapses catastrophically. When this collapse happens, in many cases a strong rebound is produced. The outer layers are blown off, and the event is observed as a supernova. After the explosion, a neutron star may remain. Or, if the remnant is heavier, a black hole may remain. Because this evolutionary pathway can be explored starting from bright, luminous supernovae, it has been increasingly confirmed by observations. And if you look at this diagram, you can also see a pathway in which a star evolves directly into a black hole, without producing a supernova. This is a theoretically predicted process. It represents a case where the shock is not strong enough to blow off the outer layers, and material can more easily fall back toward the center. In this process, there is no bright supernova to see. And observationally, it was expected that the star would appear to vanish quietly. Phenomena like this had been found before as candidate disappearing stars, in a galaxy called NGC 6946. However, the observational evidence discovered this time, by the team led by Dr. Day at Columbia University, is dramatically more compelling. The first key point is that the object discovered this time, was located in the Andromeda Galaxy. The distance to the Andromeda Galaxy is about 2.5 million light-years. This is quite nearby on the scale of the universe. That means that with instruments such as the Hubble Space Telescope, we can observe it at high resolution. We can track, with considerable precision, which star in the galaxy changed, and exactly how it changed. This image shows a specific region of the Andromeda Galaxy. The yellow square marks the area that was examined in detail. and the yellow cross marks the location of the star that evolved directly into a black hole. In the upper left, you can see images taken in the infrared. Comparing images from around 2010, with images from around 2017, you can see that the brightness at the cross changes. In the difference image, that change stands out even more clearly. This captures a temporary brightening around the star, in the mid-infrared. A mid-infrared brightening can indicate that the star's surface may have changed. At the same time, it can also indicate that more dust formed around the star. The image on the right shows the same location over time, in optical light, and near-infrared light. In the optical image from 2012, you can see a star at the cross. But in the optical and near-infrared images obtained in 2022, that star is almost no longer visible. In other words, in the world of visible light, the situation became one where the star appears to have disappeared. Meanwhile, the near-infrared images show something slightly different. At the same position, they show that an extremely faint, red light remains. Even so, it is not the picture of a bright star continuing to shine as it once did. These characteristics suggest the possibility that the star evolved directly into a black hole, without producing a supernova. However, there is still the possibility that the star did not vanish, and was simply hidden by dust. Optical light can become faint for reasons other than the star disappearing. If a large amount of dust forms around a star, visible light is blocked, and appears dim. In that case, the dust absorbs the star's light, warms up, and then shines in the infrared. So, when visible light becomes faint, a corresponding brightening in the infrared is often expected. But the observational data showed that the infrared did not brighten either. Instead, the energy emitted by the star itself dropped dramatically. Therefore, it is thought that nuclear fusion in the core shut down completely, and the star collapsed into a black hole. The research team then compared the brightness changes, like those in this figure, with theoretical models. As a result, they found that the observations can be explained by a specific model. In this model, after the core collapses, the outer layers are not blown away sufficiently. Instead, they flow inward toward the center, and pile up. If the outer layers are not expelled, and a large amount of gas falls back toward the center, the compact core left behind gains mass rapidly. And once that mass exceeds the limit that can be supported as a neutron star, gravitational collapse does not stop. So it becomes natural to conclude that a black hole ultimately formed. Signs of that process appear in the brightness evolution shown in this figure. The black and orange squares are the mid-infrared data. The other points are optical brightness measurements obtained with a variety of telescopes. The first striking feature is a temporary brightening in the mid-infrared, around 2014. Then, after some time passes, the optical light rapidly fades. And it is also important that there is no sign of a rapid, short-lived brightening, like that of a typical supernova. To satisfy all of these features at the same time, it is more natural to explain the data not by a powerful explosion that blows off the outer layers, but by gas falling back to the center, and piling up there. From this pattern of brightness changes, the final stages of this star can be described as follows. First, in the stage before 2014, the star is thought to have originally had a mass of several tens of times that of the Sun. However, it lost its outer layers through strong stellar winds. And by the final stage, it had become as light as about 5 times the mass of the Sun. Around the star, dust produced as the expelled gas cooled, was spread out. Then, around 2014, the fuel in the core was exhausted. The core could no longer withstand gravity, so it collapsed. Normally, a shock wave would form, and the star would explode brightly as a supernova. But the shock was not strong enough, and it could not blow away the outer layers completely. As a result, much of the outer gas fell back toward the center, and a black hole formed. In addition, a small amount of energy released during the collapse, or changes in the surrounding environment, can be interpreted as heating the nearby dust. This produced the temporary mid-infrared brightening. And from 2017 to 2022, the optical light faded rapidly, and the star became harder and harder to see. In other words, once the black hole finishes swallowing the surrounding material, the energy source is cut off completely. As a result, in visible light, it became more than 10,000 times fainter. It vanished, as if dissolving into the darkness of space. This discovery is not limited to simply capturing a rare astronomical phenomenon. It is an important missing link that connects two major mysteries that modern astronomy has grappled with for many years. The first mystery is the problem that there are too few supernova explosions. From the number of massive stars in the universe, we should observe supernovae far more frequently. But the number of explosions actually observed falls well below predictions. To explain this discrepancy, it has long been suggested that many stars may become black holes quietly, without exploding. This discovery provides decisive evidence for that idea. It strongly supports predictions that up to about 30% of massive stars follow this inconspicuous fate, disappearing into the darkness of the universe. The second mystery is how black holes that are tens of times more massive than the Sun are formed. In recent years, observations of gravitational waves have advanced. These are ripples in spacetime that propagate as waves. From these observations, we have learned that the universe contains many large stellar mass black holes, with masses of several tens of solar masses. Among them, gravitational waves have even been observed from mergers of black holes with masses of more than 100 times that of the Sun. However, it has been difficult for conventional theory to explain how such heavy black holes, of several tens of solar masses, are formed. That is because, if a star produces a supernova at the end of its evolution, it blows most of its mass out into space. This makes it unlikely for a heavy black hole to be left behind. But if, as in this observation, a star collapses as a whole directly into a black hole without an explosion, then the star's mass does not escape outward. Instead, it gathers into the center. That provides an excellent explanation for why heavy black holes, like those seen through gravitational waves, can be born. In this way, this observation, clearly capturing the existence of stars that disappear quietly, rewrites what we thought we knew about how stars die. It is a historic first step toward understanding more accurately how the universe is put together, and where black holes come from. I'm excited to see what comes next. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.